Hello everyone, it's December 18th. We are 5 days left. I thought it's 9. Huh? I thought yesterday was this a 93? Huh. Alright. Apparently I have done this before. Let's just reset the whole thing. Oh, it was in Python back then. Alright, we need to find all people with secrets. You're given integer and indicating there are n people numbered from 0 to n minus 1. You're also given 0 indexed to the integer array meetings, where meetings I is x, y, and time indicate that person xi and yi have a meeting at time I. A person may attend multiple meetings at the same time. A person may attend multiple meetings at the same time. Finally, you're given integer first person. Person 0 has a secret and initially shares the secret with a person, first person at time 0. This secret is then shared every time a meeting takes place with a person that has the secret. More formally, for every meeting, if a person xi has a secret at time I, then they will share the secret with person yi and vice versa. The secrets are shared instantaneously, that is, a person may receive the secret and share it with people in other meetings within the same time frame. Return a list of all the people that have the secret after all the meetings have taken place. Why do we need a person 0? Is 0 included in? I think 0 is included. You can have 0 inside this, right? So we have n is at least 2 people. Meeting is this. X, yeah, it can be 0. And these two are not the same. The time can be this. First person is not a 0. So 0 and 1 basically is your starting point, because and the 0 has a secret and it's shared with first person at time 0. So basically we have 1 and 2. We can probably, I don't know, 1 and 2 at time 5. At time 5. I don't know what would be the best way to represent this. So this is the meeting. So we have 0 times 0, and then we have 1, 2, 3, 4, 5, 6, 7, 6, 7, 8, 9, and 10. Okay, how about that? And then at this time we have 0 and 1 person have the secret, and then if we sort this by time at a time 5, right, we have 2 and 1, and we basically want to know if both already have the secret, then yeah, we're good. If we don't have to do anything. So at each timestamp, you need to check every single one of them, right, to see if anyone has a secret. Okay, here is the thing. It happens instantaneously and everybody can share with everybody else. So if I get all the people that's on this meeting, right, and then how do we know? Because I'm thinking about union find, right? This is a union. And then the next one, we're just going to union. We're going to union everybody in here. Okay, so we union everybody. And then we'll check if one of them has a secret, then the rest will have. But why would you use union find? You don't need, because that can just be a set. And I will just go through every people in this and see if it's in the set. At least one of them in the set, everybody is in the set. So in this case, 2, so we have 0, 1, 2, right? And then time 8, we have 0, 1, 2, 3, and last we have this. I'm not sure, so in this case, at time point 2, I have 1 and 2. At time point 3, I have 1, 0, and 3. So at time point 0, I have 1 and 0, right? So this is basically the starting point. Then I go to 2, 1 is in, so I have 1, 2, so I have 0, 1. Oh, first person is 3. My bad. I didn't see that. First person is 3. I thought it was 1. So first person is 3. At time 2, so none of them knows. Alright, so none of them knows. And time 3, 0 knows as a 1, 0, 3. And in this case, we have time point 1 is 1, 2, time point, and also 3. Right, and then at time point 2, we have 3, 4. And then at time point 0, we have 0 and 1. So 1, 2, 3, 4. 1, 2, 3, 4. What is the difficulty in this one? Don't know. Don't know. I have no clue why this one's difficult. A set, and then we just go through everybody. Maybe the difficulty is we're gonna have 10 to the 5. So everyone goes through at least once. That is the difficulty, I think. Because 10 to the 5, I can have 10 to the 5. They can have 10 to the 5 of this. And each one will have a set. So like you can consider each set become gigantic, right? And then at every timestamp you have to go through the whole thing. Every timestamp you have to go through the whole thing, and that is the risk. So you can run the risk of going O meeting length times the it's O n squared, right? That's why it's tough, because if you use this, it will be pretty straightforward. So you need to find another way to do this, right? So these basically are edges in a tree or in a map, right? So basically you can create a graph starting from 0 and 1, right? That's the first one. And then from 1, you want to know if I can move on, or if I can go 0, can move on, right? Like a DFS, right? Like a DFS. So you have 1. You try to see, like this. I think will be a better example. It's just at different time you'll have different at different time you'll have different children, right? And if a child has been visited, you don't have to visit again. That's the key part to this. So at this time, okay, then but each time right, you hit a time, and you sort it first. So go to the first one, you check. Actually, you can't, right? So you need to sort it, and then you go through. Not really sort it. You get it. You put a timestamp out. You get the. I think that's fine, right? Because you go through the more ones, and then you do, that's on. So you get your things together, right? And then when you go through this, that's when it becomes difficult, right? That's when it becomes difficult. I think what you need to do is, if a person is in a meeting already at an earlier time, but that doesn't mean it gets the secret at that time. It can get the secret later, right? It may get the secret later. How about we go from people, right? What if we go from people? So each person can have edges going out. And I think it probably, like, if you have a duplicated edge, so we can say a person can have go out to another person, right? That's the link. And we record the earliest time when they have meetings. So we dedupe a little bit. So it's a kind of a 2D array with 10 to the 5th times 10 to the 5th. Oh, I am not sure about that. If not that, then you just need to have a map. I might run out of memory. Okay, I'm not sure. We can actually give it a shot. I don't know. Let's call it, let's say, vector. Yeah, we're just gonna experiment. 1, 2, 3, 4, 5, right? So that's the maximum. So we say vector of vector, right? And we say n n. So that's graph, right? And then we say might as well just go through this. I want to know. This will be interesting. All right, we can say graph ij equal to, I don't know, I plus j. And then I'll return this. Wallet, memory. My bad. Yep, not gonna work. It will have memory issue. So yeah, we will have to not do it this way. Well, we can use map. I'm not sure if this is already, like, if we do have all those people, everyone has an edge. Huh. Yeah, like if you do that and then you look for the next one. What if we do a map of map? Because I do need to know when is the earliest. When is the earliest? Then what? You get this node and then you look at all the children and you push them in and then we do a priority queue. So the earlier time pops out first. That actually is not a bad idea. So what we say is, but we can have meetings, right? So we get out, we have those, and then but they can have another meeting. Yeah, but if two people meet when nobody has a secret, that's basically useless, right? So you should start from the two people that has a secret, which is 0 and the first person, and you start from there, and you look for their children, right? The people that have not met yet. So you look for their children, the earliest time they meet, and you push the earliest out, and then those are the people who have the secret, and then you start from there. But the thing is, if you do that way, you still have this trouble of having to deal with a memory issue, right? Even if you use a map, you'll still have this problem. But I guess we can try, because otherwise we need to build a graph one way or another, right? We have to build a graph. And when we build a graph, it's going to be into a vector of pairs, right? Because, yeah, a vector of pairs. And when you have a meeting with someone, then we'll put all of its children out, okay? All of its children out. And we will have all of its children out, but we need to know when will be the earliest time. That's okay. We'll do a priority queue on that. So I think it's a max heap, so we'll do the time first, and I'll do a negative, which is fine. And when we push those in, basically each link will have one. We'll push it in. Now we'll push all of them in, but that can make it big, because you have a person can have meeting with a bunch of other people, and you have another person will have a meeting with a bunch of other people, right? And then when you put all of these into the heap, right, we need to guarantee that I don't want duplicates, but this I do not know, right? This I do not know. What I can do is keep another list to keep track of the earliest time, right? To keep track of the earliest time. So if I keep track of the earliest time when, but you're still using a heap or no? Like, what would the heap? The heap is basically the queue. We know which one to pop out first, right? So we'll pop something out, and it's like Dijkstra, right? This actually looks like Dijkstra, because we pop it out, we'll check in the list to see if it's the earliest time. Oh, then we don't need a heap. We could just it's a regular queue will work, because I pop out, I'll check the time. If it's bad, I'll just ignore it until the good one comes out, and I will use that to get, and then that is the current timestamp, right? So from that point, you can get all its children, and only the ones that have, actually, I don't know. I am not sure if I need to keep track, because the point of keep track is I don't want to duplicate the same person with different meeting time in the same queue, but I think it's fine, because if the person has had a meeting, which means they have the secret, I will put that in the set. So the next one, if it shows up, it will just get ignored. Okay, but we still need to build a graph. Right, we still need to build a graph. Let's give it a shot. I think I have some ideas, but it's just, let me reset this again. It's not, I feel iffy that the time complexity, I'm not very, space and time actually, because I am going to use map. So we'll create, let's go 2092, use DFS, no, it's gonna be BFS, okay, with a priority queue, right, such that the person, the child, right, the child with the earliest meeting time gets popped first. I am worried about the space complexity. Now the memory limit, because we have to build a graph. We'll see. Feel like this, but well, I'm not sure. We're gonna give it a shot. So essentially, we need to first do a, either can be another map. So the int, what is this? This has to be a pair, right? This has to be a pair of int and int. We call it graph, okay? So the child is equal to, the child is meeting time and a person, right? So we say for const auto m of meetings, okay. I mean, the first thing would be when you say graph 0 dot, that's not true. It should be a vector of this. See, this is like we just keep adding more complexity on top of it. Dot push back. So meeting time is 0 and the person is first person, right? And then also graph first person dot push back. This is going to be 0 as well, and then 0, okay? And then here we have 3 values, x, y, and the time. So we basically say graph m0, okay, dot push back. Oh, hold a second. I think I need this. Oh, that's fine. It's negative meet time, right? Negative meet time. Okay, so child is negative meet time. We need the timestamp to be negative because the priority queue is a max heap, if I remember correctly. Alright, so here basically negative m2 and then m1, right? And graph m1 push back negative m2 m0. Alright, that is to build a graph, and then we'll say priority queue, priority queue of, I actually forgot how this one is. I think it's, we're gonna put pairs in them, right? So PQ, yeah, max heap, right? Max heap, and what we're gonna put in, we are going to put in, actually, why do you do these two? I think these are useless, right? These are useless. You don't need these. Here we do need to get max heap dot push, right? So 0, 0, which is the time and the person, right? Time and a person. And we also need to push 0 first person, right? So these are the two people first in it, and then when they pop, because it's max heaps 0 pop first, okay, which is fine. And then we need an ordered set. Okay, we call it int. We call this is visited. Okay, the visited people. And we say visited dot. Actually, no. And we need a vector of int, which is result. Okay, so we say while max heap dot empty. If it's not empty, right? So we say if visited dot contains, right? Dot contains max heap dot top dot second, right? If it does not if it contains, then right, if it contains max heap dot pop and continue. Okay. Otherwise, it does not contain, then we can get the time. We don't need to get a timestamp out because the timestamp will always be the smallest. And we'll get the person is going to be max heap dot top dot second, right? And then we'll get all its children. So we have this, and we have t is max heap dot top dot first, right? But it's gonna be a negative of that, and then max heap dot pop, right? It's also gonna get popped. All right, so now it gets popped. So we are going to add it. So visit dot add this person, right? And then for const auto c of graph dot p, the people, right? Insert, I'm pretty sure. All right, so c is a vector. Now graph p is a vector, c is its children, right? Pairs. So c dot first is the time. I can just push c directly in it, but I need to check, right? So the check is if visited dot contains c dot first, not c dot second, or yeah, we do the insert when we visit. So if it contains, then we don't do it again. That's actually, I mean, that's fine. It's fine, but usually I don't think this will hit anyway. Or the time is earlier, right? If it's earlier, then it means you don't have to do it again. So we say, or the current time is t. So if c dot first, actually let's not do the negative here. Let's do the regular here, just the time. Yeah, it's just the meeting time. Okay, it's just the meeting time. So blah blah blah. We get the, but when this pop out, it has to be negative because it's pop out from the priority queue, from the max heap. So c dot first is the time, right? Meeting time. So c dot first, the meeting time. If the meeting time is smaller than the current time, if these, then we continue. That means we have visited already. In fact, I think this shall go first because the likelihood that this one gets hit is very high. Is very high. So we go first and then we say or. We're then going to continue, right? Otherwise, that means it has not been visited before, so I need to push it in, right? When to push it in, so we need to say max heap dot push negative c dot first, right? Negative c dot first and the c dot second. C. Yes, here. Right, for every children, we say if the time is earlier, then it's not going to be good. Or if it has been visited, right? It's also not going to be good. If none of these, then we're going to push it in, right? We'll push in, and then we will go through blah 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 and then visited p, and then also I think res dot yeah, I can turn this into, yeah, I don't need this, I just use visited, right? So blah 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 once we're done, and then it will go for the next round. So once we're done, we'll return vector of int. Not sure if it's visited dot begin, visited okay, let's see if it works. It's already 33 minutes, so we'll just run it. If it doesn't work, then we will copy and paste. Alright, let's see if it works overall. Oh, it works. Then it's not really that hard. 236 milliseconds, 44.1. It's not, the performance is also not that bad. Alright, take a peek. Blah blah blah. Blah 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 blah. Alright, we have a map, so this is to do a graph, that's fine. Earliest a vector, size n, so you know when is the first time. So you got a q, and then not empty, BFS, So you keep track, this one keep track of the earliest time. So you go through the graph, the next person, you update all of that to see which one has the earliest time, then you go, and at the end you do that. So it's just BFS. How do we use earliest? If t is larger than the time, which is the current time, and the earliest is larger than earliest next person equal to t. Wait a second. I think this part I'm not quite sure if I understand. we have the person and time, right? So q.pop, yes. So we get the next person and the time. The time has to be larger than, yes. The time has to be larger than, because it's earlier than means, yeah, I think we have a similar, and we have similar logic around here, right? We have a similar logic. So time is a larger than, and the earliest person, the time is larger than t, yes, so because we want to keep track of the minimum. So we go through everybody to keep track of the minimum, so we get a minimum time, we put that in, and and then we pop out the next one. So this guarantees when we visit a person, all of his children, we only get out the earliest one. And if we meet another child, another one again, and it's earlier time, then we don't, and we ignore it. And once we're done, because we get all of them is the max. So as long as it's not equal to max, it's yes. Yes, it's the same idea, but I think this actually might be faster, right? I think this is actually faster because they don't have this heap. I'm using a heap, but I guess it's fine. I think they also have a DFS solution, which I'm not gonna worry. Do they have a union find? Earliest informed first traversal. Ah, you got a priority queue. Looks like this is our solution. If visited, we say visited is true. Now visited, and then we put it in. Yep, I think that's the same thing. Yeah, oh, okay, the only difference is they use a greater, so I don't have to do negative, but I have to do negative. They put a pair, I put a pair, so they use this to get it out. Yeah, I should do that too. And they get a vector, which is fine. If you look at this, this is to get it, right? And then we'll continue. They get it out and they pop. Actually, I think that is a better way, so we can save some lines. Then visited, and then we do this, and then we, yeah, it's exactly the same. Breadth first search on time scale. Whatever thing that is. Oh my god. Ooh, union find with reset. Oh, I seem to remember this. I think there's one more. I don't know if there's one more. That's it. All right, let's see. Oh, I think it's pretty nice. I think this is the first time I tried it. I union find it. Okay. And second time, I don't know, I didn't solve it. And I solve using BFS. So it is likely that this is the first time that we solve in the first shot. It is very likely. And previous, it's 55 test cases. See how many test cases? We got 57 test cases. Not bad. So we are on the right track today. That's good. That's very good. All right, that will be it. We have